Thanks everybody for joining us today. I'd like to thank the Royal Institute of Navigation for facilitating this webinar for us. So the subject today, risky business, ensuring precise time for critical infrastructure. I want to talk a little bit about the reliance on satellite navigation systems as a source of time, using GPS as an example, seeing as it's the most used satellite constellation out there in terms of timing receivers. Some of the issues around using satellite navigation signals for time, in terms of a cybersecurity perspective, maybe some of the attack vectors for time systems, what the bad guys might try to do, how they might try to do that. Some of the risks, how we might assess them, some of the frameworks for assessing risks, quantifying them and how we deal with them, and most importantly, the mitigation strategies that we can put in place to ensure that we protect our time generation, distribution and dissemination resources. Before I do that, before I get stuck in, just a couple of really quick slides to introduce Chronos. If you're not familiar with the company, Chronos Technology, a UK company based in the southwest of England, formed in 1986 by Professor Charles Curry, who's still the owner and the MD of the business. We are a technology-focused company, a system integrator with specific skills and expertise in synchronization and timing and frequency systems. We are a reseller. We resell products from a company called Microchip that in the past has been known as either Symmetricom or Microsemi. Those companies were acquired now by Microchip. Those companies make atomic clock, GNSS references, clock distribution systems like NTP and PTP servers. We resell those and support them in the UK, Sweden and Denmark. We also have a knowledge business that does training. We do consultancy, as Claire mentioned in the intro. We work with network operators and vendors to plan sync and timing networks. We're involved in the standards as well, the ITU Study Group 15, question 13. We are on steering groups of various bodies. My colleagues are on the steering group for the Royal Institute of Navigation. I'm on the steering group for ITSF. We have R&D and development, and we sell, install, commission, support, and do training for these products into all the market sectors that you can see on there: telecom, power, financial services, defence, law enforcement, and broadcast, to name but a few. We have our own team of installation and commissioning engineers and our own support engineering department. The guys who have installed and commissioned GNSS timing systems have done that all over the world. This little map just shows some highlights of where Chronos has installed GNSS timing systems. And our excellent support team support these systems 24 hours a day, 365 days a year. So lots of the experience and the expertise that we have in supporting these timing systems is what we've gathered to put into this presentation today. So to get stuck into the subject material, to set the scene, this is a book that I was reading on holiday last year. This was my holiday reading. Click Here to Kill Everybody, a book by the well-known, well-respected security researcher Bruce Schneier. In the book, he talks about our hyper-connected life, the way modern life is connected. Everything is connected to everything. One of the significant things, the points that in the book that he mentions that I pulled out, is everything is now a computer. So we're aware really of our smartphones, excuse me, smart speakers, smart thermostats, things in our houses that we can see are computers, but really everything, cars and trains are computers. If the engine management unit on the car detects a fault, it won't let you start the engine. The car won't go anywhere. It's not a mechanical device with some computers around it. It's really a computer with some mechanical extensions. The title of the book, Click Here to Kill Everybody, really comes from, he's talking about medical electronics like pacemakers and insulin pumps. These things are really computers with Bluetooth and Wi-Fi, but they just happen to be controlling sort of critical medical functions. All computers can be hacked. So it's a fundamental thing that all these computers, they're fundamentally insecure. And current software development strategies doesn't really help this. You might be familiar with this sort of classic, this development ideology that's attributed to Facebook, move fast and break things, where we're continually deploying code, continually deploying new versions of code to patch things. It doesn't matter if it's not quite right, we'll get something out to the customer. If it's wrong, we can patch it later. Everyone's familiar with their smartphones and their laptops continually requiring software updates. And it's part of that overall software development methodology that is at odds with traditionally safety critical, mission critical, life critical software development. Was always a long development time where code would be written, tested, retested, modeled, stress tested before it's released, which is at odds with the sort of current software development. And you might say, well, okay, critical national infrastructure doesn't run on smartphones and things, but the people who are supporting it, it's the humans that are always the weak link. The people that are supporting these networks have smartphones, have laptops. And it's often been shown that the way cybersecurity attackers break into secure networks is by breaking into a smartphone first or somebody's laptop computer first. So it is a significant issue. And the last point of the book is cyber war is the new normal. There's this constant on the internet sniffing of open ports on devices, looking to try and identify what's at the end of an IP address, constant probing and constant attack. So really setting the scene for the theme of this talk in that cybersecurity way. Time is often referred to as the invisible utility. It's something that we sort of take for granted, but it really cuts across many sectors of modern, industrialized, modernized economies today. So there's a whole series of industries here referred to, starting with the railways back in the 1800s, when each town had its own time. Each town had a solar timescale based on, they would survey the position of the sun. When it was exactly overhead, that was noon in that location. Obviously the railways came along and they realized they had to use then the same timescale across the whole country to stop accidents. There were lots of accidents with trains being on tracks, two trains trying to go in opposite directions on the same track because they made errors in time. So transport starts us off there, really goes through even to modern day smart motorways, smart infrastructure, not just the road network, but also the rail and marine, maritime navigation and shipping all require precise time. The telecoms industry, which is where I started my career back in the late 80s. The telecom industry in the 80s started to use atomic clocks as a frequency source to stabilize the primary reference clock for telecom networks. This is an R&D lab back in the 90s where we were investigating some issues with synchronization because of modernization. And right up to the present day, this is a photograph from the 5G trials that were going on last year. This was the EE trial in London of 5G, and you'll see in the slide there's a GPS antenna, a GNSS antenna at the top of the pile, because 5G has very, very strict time alignment requirements. So again, it's to do with maximizing the efficiency of the radio resource, getting the maximum bandwidth out of radio resource. And also some of the new functions in 5G, like beamforming antennas, they require very tight time alignment at the antenna array itself. So for that reason, 5G particularly requires accurate time. Financial markets, financial trading, we start to now see, again, time being a requirement to underpin these industries, and also for regulation. There are regulators both in North America and in Europe that require financial trades to be time-stamped, to be traceable back to a legally verifiable timestamp, and that usually means UTC, Coordinated Universal Time, the global timescale. So voice trading, the accuracy required is about half a second, but for machine algorithmic high-frequency trading, in Europe, the requirement is 100 microseconds. All these trades have to be timestamped to within 100 microseconds of a legally verifiable source of UTC. The power industry is going through a revolution at the moment where rather than centralized generation flowing power out to the users, there's now micro generation with solar, wind, and geothermal. And the grid, the distribution, the transmission grid is evolving to accommodate that. And most of the time that involves, the so-called smart grid involves making measurements of voltage and current at different locations and trying to work out, in the worst case, if you have a short circuit, if you measure lots of current going in the end of one link and no current coming out the other at the same time, then you're pretty sure you've got a short circuit somewhere. So again, time is critical for the power distribution industry. Broadcast, digital video broadcast, DVB, terrestrial television, and digital audio broadcast, the transmitters all need to be synchronized as well. So they need a stable frequency reference and they need to be time aligned. It's a packet-based, time frame-based transmission system. And also this diagram here is just a generic one that I just stole off the internet to represent artificial intelligence, big data, and smart anything else. There's lots of buzzwords, lots of things flying around, particularly big data. And lots of the ideas and the processing of that data that I've seen, lots of it is reliant on time. If we have a database full of data and the time is corrupt, if an attacker can somehow spoof the time and taint the time, the data is effectively thrown away. So again, even these modern concepts, very modern buzzwords like big data, they require accurate time. And the source of that time for all these industries really over the years has developed as relying on atomic time from satellites, distributed by satellites from GPS and other GNSS systems. So a little bit of terminology to get us started. GNSS is a generic acronym that describes all of the satellite navigation systems. GPS is the American system. This is taken from Wikipedia a few days ago. It talks about GNSS being Global Navigation Satellite System. And it lists the operational systems. It lists the American GPS, it lists the Russian GLONASS system, and it lists China's Beidou system. Rather cruelly, it relegates Galileo to not being fully operational. It talks about it being scheduled to be fully operational, but it's not in there. But again, GNSS is a generic term. I might say GPS when I mean GNSS, but GPS has been around the longest. Declared fully operational in April 1995, so it's been around a good 25 years, just over. So what's the problem? Well, this goes back to a quote that I heard from the chief scientist of Symmetricon at the time. So it's going back a few years now, and he used to combat any discussion about which was the best source of frequency and time to use. Anybody that didn't want to use GPS, he always came back with this quote: "It's free and it works everywhere." And that's a pretty compelling statement. In you don't have to pay to use it, and it works everywhere, and that means globally. The photograph here is of a China Mobile 3G base station. This was a few years ago. This was about 8 or 9 years ago. I was over there with one of our partners. We were reselling some test equipment that we made through a global partner, and they were trying to sell it into the Chinese mobile market. We were doing some measurements here, and the Chinese at that time very politically opposed to using GPS, but the 3G base station inside this cabin was using GPS as a time reference, as a sync reference. So even though they were opposed to it, it was actually using it. I mean, that still may not be the case now. They may have moved on to other satellite constellations, but making the point that there's this proliferation of GPS receivers all over the world. More than a few billion. I know there's a usegalileo.eu website that has a counter on it that's constantly ticking up of the number of Galileo-enabled smartphones that are in service. It's currently about 1.5 billion. So in terms of GNSS receivers, there are billions of actual receivers out there. Obviously, not all of them are embedded in critical national infrastructure, but you see there's this proliferation, and it's the de facto time source system. So to come back to the quote, it's free and it works it works everywhere. It's free and it works everywhere all the time. Part of the problem with GPS is its phenomenal system uptime. It's performed phenomenally well over those 25 years. There have been a few major issues. It's not been absolutely perfect. SVN-23, satellite vehicle number 23, has been involved in a couple of those, 2004 and 2016, different problems, but coincidentally the same satellite. And there have been a few other issues as well, but you could probably count them on, less than the fingers of one hand. And GPS is often a fit and forget module. So it's a time component that's put into a subsystem that might be integrated into a large system. The photograph here is of some protection relay equipment in the power distribution network. And again, there's a GPS receiver in here that's used for time. The time from it goes into sampling current and voltage. And again, it's this attitude that you ask an operator, do you have GPS time vulnerabilities in your network? They might say no. They might not realize that they have GPS-based time receivers buried in equipment like this. Another quote as well I picked up a couple of weeks ago from the Marinav webinar that was also hosted by the RIN, Dana Goward, I think, said, GPS has us all addicted to Stratum 1 time. Stratum 1 is a reference to NTP, the Network Time Protocol. So one of the oldest internet protocols, been around since 1985, synchronizing computer clocks on packet networks. And Stratum 1 is a reference to the NTP server that is connected to the source of UTC time. So it's easy. I've got a Raspberry Pi just over my shoulder here with a uBlocks evaluation board hooked up to it, and it is doing this function exactly that. It's providing Stratum 1 NTP time. So part of the problem is this proliferation and this excellent service record of GPS. I want to really quickly now go over what GPS is and how it works. This isn't a replacement for a full tutorial. There are other excellent tutorials and textbooks and training material out there on the internet. GPS is a satellite constellation of radio navigation transmitters. They're medium Earth orbit, so GPS is 20,000 kilometers away. It's not geostationary. That's a common misconception that I come across occasionally. People think they're geostationary. You point an antenna somewhere in the sky and the time is always there. They're not. They move around in the sky. If you could see them, you would see them rise and set and move overhead. A significant thing is the power output is low. These satellites are solar powered, so power is scarce. The transmitters on them are typically tens up to at most maybe a couple of 100 watts. So by the time this transmitted signal gets to the surface of the Earth, it's below the noise floor. And that's a very significant issue. It's a very fragile, very low level signal. The noise floor, thermal noise, is around minus 110 dBm. And the received signal outdoors is generally between minus 125 and 130 dBm. It's a coded, it's a spread spectrum signal. So the signal processing in the receiver runs correlators. There's a pseudo random bit sequence that's on there that the receiver knows. So effectively the receiver is moving itself around in time and frequency and looking for a correlation peak in this noise signal. When it sees a peak, that's when it's locked onto the signal. Like many other radio navigation technologies, GPS is a ranging system. So we have our three coordinates, three-dimensional perpendicular axes, X, Y, and Z. And the GPS receiver is just really trying to estimate how far away it is from a satellite. So if we can decode a signal from one satellite, we get the surface of a sphere as a possible, we could be anywhere on that sphere. With two satellites and then three satellite signals, we end up with the surface of these three spheres intersecting somewhere, and hopefully that computes to our user location. There is a fourth unknown. There is a bias or a clock offset in the receiver itself. So one of the reasons why we can use GPS as a timing system is the receiver's internal clock gets calibrated to and steered in some cases and corrected to GPS system time. And GPS system time is traceable back to UTC on the Earth. So again, it's a radio navigation ranging system that we can use to find out where we are and also get time. It was designed as a military system, so it was designed as an ordnance, as a missile guidance system. Obviously, you need much higher accuracy. You need to be sure where you're sending the missiles. The military have access to other signals on different radio bands that are encrypted. So military receivers have these SASM modules in them selective availability anti-spoofing module. They also use another band, L2, L1 and L2, L1 being the civilian frequency. So the military receivers are higher accuracy, and they're less susceptible to sort of sophisticated spoofing attacks because of the encrypted nature of the signal. All the civilian receivers, so all the infrastructure that you know, the sat-nav in the car, the Google Maps in the phone, all the timing receivers that you've ever seen, that you've ever deployed, all the civilian infrastructure is all built on this course acquisition code that's on L1. GPS, as it's been modernized, and Galileo and GLONASS and these other satellite constellations, as they've come along, they use slightly different frequencies. So there are different frequencies available, but they're all very close together, really. And the civilian receivers, it's only recently now that we're seeing dual frequency receivers. One of the benefits of using a dual frequency receiver is that one of the unknowns in the pseudo range is the delay caused by ionization in the upper atmosphere. And with a dual frequency receiver, you can make an estimate of that or cancel it out. So single frequency receivers do suffer from that problem, but we're now seeing more modern multi-constellation receivers that have that. But it's important to draw attention to this difference between civilian and military receivers, that the military have this encrypted signal. So a timing receiver, what does it look like? Now this is a grossly oversimplified view. Apologies again to all the academics and people who study GPS who have seen block diagrams of GPS receivers, or GNSS receivers in general, and are used to seeing about 3 or 4 times as many blocks. This is my very, very simplified block diagram. So we have some sort of radio front end where we have an antenna, we receive the radio signal, there might be automatic gain control in the front end. We then might have some A to D, and we have the navigation solution that has those correlators that I talked about, where the receiver is looking for if it can spot a correlation between the pseudo-random bit patterns that it thinks it should be seeing and what it's actually seeing. It moves in time and frequency looking for those. And the position solution, the navigation solution, is what gives us position, date, and time. In a timing receiver, we have some sort of oscillator, some sort of output stage that gives us a physical clock output. So if this is a frequency reference, it might have a 10 megahertz output. Some of them have 1 pulse per second, 1 PPS, that is synchronized to the top of the second, to the UTC second. When if you were counting nanoseconds, whenever that would reset to 0, that's when the 1 pulse per second tick happens. So that's what a timing receiver looks like. But going back to when these things started to appear commercially, so that's sort of mid to late 1990s, when you could buy a frequency reference that was based around this technology, it was not thought likely or feasible that the signal would be spoofed. It was not thought, not completely impossible, but it was not thought it was, likely to happen. So for that reason, these receivers, I refer to them as dumb receivers. They just trust the signal from the antenna as absolute truth, and there's no signal analysis that goes on them. If you can spoof the GPS signal and you can steer the time, then you can end up steering this oscillator and controlling time, and that's what we're going to talk about a little bit later. And this is obviously there is this massive installed base of these receivers that operate in this way. In the telecom industry, as I mentioned, these frequency references were available in the late 90s, early 2000s, and there was an ETSI standard, a planning guide, this EG 201793, that was released in 2001. There was lots of sort of anti-GPS, maybe anti-GPS is a bit too strong, but there was lots of pragmatic common sense advice about relying on GPS solely as a frequency reference. Now, up until then, telecom networks had used atomic clocks as frequency references. Then GPS came along. This planning guide has these 3 different types of primary reference clock. The middle one is all radio based. So you could have GPS receiver, GLONASS receiver, and maybe a low frequency, like a DCF 77 receiver. But this had, as I said, lots of pragmatic common sense advice in it. And this was the combination PRC, as it's known. This was, at that time in the late 90s, the sort of big operators, the big fixed wireline operators like British Telecom, Deutsche Telekom, France Telecom in Europe, they all went for this sort of arrangement. They realized the utility of GPS, but they backed it up with atomic clocks. And obviously this was in the core of the network where they were able to do that. Unfortunately, one of the side effects of smartphones having location in them is now really jamming is now a civilian activity. So going back to those first design requirements on the timing receiver, that jamming or spoofing might be something that would happen every day. A Facebook ad here that I screenshot, this is from a couple of years ago, selling vehicle tracking. So this seems to be the biggest driver for low-level sort of privacy reasons behind jamming. You can go on eBay, go on the internet, and you can find these so-called privacy jammers, these little things that fit into the auxiliary socket in a car. These cheap and nasty things have something like a 555 timer chip in them. It's so inaccurate, it can't hit the GPS band exactly, so these things have to sweep across the band to make sure that they hit it, but they're tens of milliwatts in some cases, and it's enough to knock out GPS in the local area. And as people are worried about being tracked by their boss, or being tracked by Apple or Google or whatever, all these various conspiracy theories, they're now seeing more and more incidents of jamming. We've got a system that we've had for many years called Sentinel, where we've had probes around the country next to critical infrastructure looking for jamming events. I know there's a Nottingham Scientific research program, Strike 3, that followed along similar lines, that measured the number of jamming events, and these things are only getting more and more prevalent. With lots of these vehicle trackers, they don't just have a GPS receiver in them, they have some sort of backhaul channel, they have a radio modem so that your location can then go into a database somewhere. So some of the more sophisticated jammers also jam 2.4 gigahertz, so they jam Wi-Fi and Bluetooth, and they also jam 900 meg or 1800 meg or 2.1 gig, so they jam the 2G and 3G frequencies. Because we make and sell interference detection systems, and we have some handheld interference detectors, we sell those to law enforcement and government agencies. And we get to see some of the jammers that they confiscate, or some photographs of the scenes where they have, and some of the really scary ones are like this one in the bottom right hand corner. This was sort of a huge crate that contained this one. It's all heat sinks and fans, so there's a lot of power being generated, and it's jamming all the cellular bands, it's jamming all the GNSS bands, it's jamming 2.4 gig. It's also jamming other radio bands that lots of high-end vehicles that are fitted with dedicated trackers that use other frequencies to communicate, it's jamming those as well. And these were discovered at the scene of organized crime, where they were disposing of stolen cars and turning them into parts and things. So it is a real issue. Unfortunately, spoofing is now a civilian activity as well. So if we consider the advancement in technology, this is, if you can see this on the webcam, this is a handheld navigation receiver from 1999. This is a Magellan GPS 315. This is a 12-channel GPS-only navigation receiver. It takes about 5 minutes to get a fix. It runs for, if you're lucky, 5 or 6 hours on 2 AA batteries. And say it's 12 channels, so it can only track 12 satellites. From 1999, so 20 years later, the modern smartphone, this is Samsung Galaxy S10. You can look on the internet for a teardown of it. People will take these apart when they come out, phone handsets. You can see what's inside it. It has a Broadcom chip inside, a GNSS chip, a multi-constellation chip. The most number of satellites I've seen this one track is 38 at one time, and it gets a fix within 3 seconds when it's outside. So the technology has increased over 20 years in the receivers, but also spoofing technology has developed at the same pace. So spoofing is now trivial with commercial off-the-shelf hardware and open source software. So last summer, I wanted to see exactly how easy it was to build a spoofer. I'd seen lots of demos. I know DEF CON and Black Hat sort of hacking conferences. These engineers have been talking about spoofing GPS probably for 5 or 6 years or more with software-defined radios. So I knew it was possible, but they were just putting in any old position or any old time. I wanted to see if it was possible to build a GPS spoofer that I could synchronize the time close enough to actual UTC time that I could then take over a timing receiver and gently steer the time away. And of course we could. We did that. We tested this in our lab. The big problems that we saw were taking over the time in a timing receiver and speeding up our clock so that time appears to go faster to the receiver, and then stopping the spoof so our signal goes away. As far as the receiver is concerned, then time jumps backwards. Lots of these timing receivers, the firmware, the software in them had not been written to obviously ever contemplate that happening, and some of them crashed, the firmware crashed, and they needed a power reset. Some of the work that our colleagues did, colleagues in the BBC and Arqiva in the UK, they, using a bigger simulator, did similar experiments, and they spoofed time a long way in the future and past. They spoofed sort of 20 years forwards or backwards. And I think the fault that they saw may be related to the GPS weak rollover issue, where the weak number in the GPS system is a 10-bit number, so there's 1,024 possibilities, which is about 19 and something years. So if you go over that time, you're effectively forcing the receiver, and they actually managed to brick a receiver. This was a brand of receiver that was deployed in critical infrastructure locations, and they managed to spoof the time to it to such a degree that it needed to go back to the manufacturer to have its firmware reprogrammed. So again, attacks on critical infrastructure could vary from the really subtle attacks, where I'm thinking of what's the nuisance, trying to get in, trying to think of it from an attacker's perspective. What could we do to really mess with this critical infrastructure? We could blow it up, we could burn it down, or we could do something really subtle and try and cause problems between different parts of the network. So these sort of subtle plot errors are what I was thinking of. Again, mobile infrastructure, 3G, 4G, and 5G uses GPS at the edge of the network as a frequency reference, and ultimately the radio frequency that it transmits on is traceable back to that. Could we interfere with the frequency to such an extent that we could cause interference between mobile operators? As I've said, causing a single failure, critical national infrastructure has already some degree of resilience in there. So again, a single failure is maybe not a big thing. But again, trying to put lots of these little subtle attacks together and coordinating, again, maybe at either ends of a power transmission line. If we steer the clock at one end slightly forwards, steer the clock at the other end slightly backwards, get a big enough time difference between ends of this transmission line that the sampled values of current and voltage start to disagree. So can we shut down that transmission? Is that something that could happen? Can we hack access controls? Can we spoof the time, that it's the weekend and people who are trying to get into a building can't get in because their passes aren't valid at the weekend? All these sort of concepts. In terms of the risks, with sync and timing, it's always a question of what's the accuracy that you actually need. There's no point deploying atomic clocks if you only need a second or half a second of accuracy in your time system. So again, in terms of what the risk looks like, it's how much accuracy do you need and how long do you need that accuracy to be there if GNSS is denied. And then we get into discussions about holdover. Holdover is a term in the timing community for when your reference source is gone, how long can your local clock maintain the accuracy that you need? So that leads into questions like, do you have miniaturized atomic clocks like rubidium clocks, or is an ovenized quartz enough? What sort of interference? We talked a little bit about jammers, spoofers. There's also unintentional radio interference, other radio systems that are transmitting where they shouldn't be, or they're not configured properly, accidental things that fail. Sometimes active antennas on the roof get water in them and they start to oscillate and start to re-radiate. Or is it natural signal interference, space weather and things like that? So we can plan for most of those outages, and you wouldn't, because of the fragile nature of the GNSS signals, you wouldn't necessarily rely on them all the time. You would build in some sort of holdover to any systems. And critical national infrastructure should be pretty well risk assessed. And we've been talking to people about critical national infrastructure for 10 or more years in terms of time and timing and reliance on time sources. There are frameworks out there already to risk assess, to do a risk assessment. So there's the National Cybersecurity Centre, the NCSC, the CAF, the Cyber Assessment Framework. There's also ISO 27001 and ISO 31000 business processes that look at risk assessment. So there's all these things there. Part of the problem, I think, is that the bottom few bullet points there make the point that in the 1990s, the revolution that telecom core transmission networks went through was they created a standalone timing architecture. So the timing wasn't just embedded in the traffic anymore. They had a separate physical entities that were primary reference clocks. And these other entities, SSUs and SECs, they were nodes within the network. But if you were doing a risk assessment audit, you would physically see the clock there. It would be standing in front of you. It would be plain that there's a reference clock. The problem, I think, is what about the invisible clocks? What about the clocks that are embedded in other things? My car's got a GPS receiver in it. It uses it for the sat nav. It tells me the time on the dashboard. Does it do anything else? If there's an emergency and I press the emergency button, does it time stamp the call and things like that? I know Tesla, the electric vehicle manufacturer, they have 3G modems in their cars, and they can enable features in the car. So the performance of the car can be changed, the navigation package can be changed, whether it can supercharge, whether it can charge quickly or not, can be remotely enabled and disabled. So Tesla has this model of being very much in control and knowing exactly what's going on in the car. What about the timing receivers in there? What about the GNSS receivers? Could we spoof GNSS time if we spoof it 20 years in the future or 20 years backwards? Would that Tesla start? Would it drive, or would it rely on something else? The photograph on the right as well is a Panasonic Toughbook. This is a laptop, a ruggedized laptop, one of the only laptops that actually contains a GPS chipset in it. But it happens to be the type of laptop that you often see field technicians using. So technicians that would go out to site to repair critical national infrastructure, they might be using one of these. What happens if we spoof the time in this? Can we get the laptop to crash? It's not just attacks on the critical infrastructure itself, it's the supporting infrastructure. Can we stop somebody's electric vehicle from going by attacking the time, or stop their tools that they do their job with by attacking the time? There are anecdotal stories of navigation conference a few years ago where one of the technology exhibitors was accidentally radiating a GPS, a GNSS signal into the exhibition hall, and lots of people's iPhones displayed this sort of screen. This is, I think this is a much older version of iOS. I'm not sure whether this iOS would behave like this now. But certainly, again, it's that issue of trust. If we're employing field technicians and they have iPads, and the iPad is their secure way of accessing a corporate network, or maybe going to site and diagnosing and fixing problems with critical infrastructure, there could be some collateral damage from a time attack, a time spoofing attack using GNSS to cause mayhem in these support systems. So what can we do? I spent a long time talking about the problems. What can we do to fix it? Well, one of the sensible things seems to be this system of systems approach, and this goes right back to the 2001 ETSI planning guide that I pulled out those diagrams of the primary reference clocks. We don't just rely on one signal. We don't just rely on satellite GNSS time. We build our systems to have technologically dissimilar inputs, so they're not affected by the same the same weaknesses, the same vulnerabilities don't affect all the systems. Highly available, highly redundant systems. There's all sorts of methods and methodologies for doing this in all different fields of engineering. I understand this is a picture of an autopilot system, and these three boards here are three identical copies of effectively the same computer. I understand that the way this, obviously in the aviation industry, this is life critical, safety critical autopilot software. This is the stereotypical view that the pilots are sat in the pilot and the co-pilot are sat in the cockpit drinking a gin and tonic, not looking where they're going, and the computer is flying the plane. Now, the software development, I understand that they have three physically separate teams developing the software for each one of those instances of the autopilot function, and they use different software tools, maybe different software languages. And again, that's that critical appraisal. And the system of systems is, if there is an error in the compiler or some data or memory leak that's apparent in one of those systems, hopefully it's not apparent in the other systems. And again, it's that similar philosophy of using this system of systems approach. And there are lots of reports already published. There's a Volpe report from North America in 2001, the Blackett report in this country, which has been updated a couple of years ago, Royal Academy of Engineering, and a London Economics report that looked at the economic impact on the UK economy of GNSS as denial. So there's lots of excellent work that's already been done. So what can we do? We're talking about building a system of systems of timing receivers. So what about other satellite signals? We know our sat-nav systems. What about geostationary or low Earth orbit satellites? They could be useful. Inmarsat have a network of geostationary satellites that are primarily used for comms, maritime and aviation comms. They supply some of the backhaul for in-flight Wi-Fi, satellite phones. Because these things are geostationary, there's a fixed latency between a stationary receiver and the satellite. So they could, in theory, be used to send timing messages over them. Low Earth orbit satellites, there is Satales that provide STL, satellite time and location. This again is a low Earth orbit. They're about 500 miles altitude, so much stronger signal than GPS, about 1,000 times stronger signal. So therefore it will actually, you can receive it more easily indoors. It's an encrypted signal as well. You need a special receiver to receive it. Obviously, it doesn't work with existing GPS, GNSS receivers. And the accuracy, because of the high signal strength, once the signal gets inside, there's lots of multipath reflections. So the accuracy of STL is quoted, I think, around about plus or minus half a microsecond, plus or minus a few hundred nanoseconds. So depending on the accuracy, it might not work for that. And of course, I have to talk about OneWeb. OneWeb has been in the news a lot recently. The UK government's aspiration to take a stake in this this low Earth orbit, currently broadcast satellite network. The satellites that are flying at the moment have KU band radios in them, not designed for sat-nav. I've seen lots of discussion on the internet, very insightful piece that I found talked about the challenges of using these satellites for sat-nav. For a start, there's hundreds of them in the constellation, so do we have enough atomic clocks to build on the Earth to fit into navigation payloads to go in these satellites? Another idea in the same piece was saying that maybe we should put GNSS receivers in the OneWeb satellite so that they are a few hundred miles in altitude, so they've got a clear view, direct line of sight view to the other GNSS constellations. You could have a smart receiver in there that could do timing measurements and quality of signal analysis and work out if all the constellations are working, and create its own time base and then rebroadcast. Whether it's going to rebroadcast in a GPS-like signal or completely separate is still open to discussion and part of the challenges that lie ahead. Other radio signals that we have access to, low frequency radio signals, ELARAN, a terrestrial based navigation system, low frequency, so again 100 kilohertz, very powerful transmitters, in some cases up to or getting close to 1 megawatt. Not a global system, so again it would be local. The North American system was turned off a few years ago. The Timing Resilience Act that was recently signed a couple of years ago looks at replacing that with a new system. Again, technologically dissimilar to GPS, so low frequency, high power. So if you wanted to jam or spoof this signal as well, you'd need a much bigger antenna. Even a whip antenna for this would be quite large and a lot more power. So again, you'd be conspicuous, so you might draw attention to yourself from the law enforcement agencies. And there are a whole raft of other local low frequency radio time signals. So from Europe, we've got MSF in the UK, DCF 77 in Germany, TDF is a French signal. North America has WWVB. And there's also a BBC radio transmission on 198 kilohertz. Actually contains a timing signal in it. It used to be, I'm not sure if it's still operating, whether this economy 7, it used to be cheaper electricity in overnight. You'd have special storage heaters in your house that would turn on when they receive this signal to balance the load on the grid, heat these big storage heaters up in the overnight period to then slowly release heat into your home. So that there are other radio signals available. But we do have network distribution of time. We have telecom networks, we have mobile radio networks. They use GNSS in the core. They also have backups of their atomic clocks. Synchronous Ethernet is a technology that can synchronize the physical layer. So you could have a BT OpenReach box deployed in a business or in a consumer premises that could deliver stable frequency via synchronous Ethernet. And also these packet timing protocols. I mentioned NTP before. The precision time protocol, IEEE 1588, has been updated last year, is more accurate than NTP. It has hardware timestamping assistance, and you can send up to 128 sync messages per second. There are other systems for TikTok is a new protocol that's being looked at for data centers to synchronize servers and computers around data centers. IBM SDP is a proprietary one, but we have physical infrastructure that we could utilize as well, so not just radio signals, which leads nicely into the National Timing Center program. So this is an NPL initiative. There's an announcement on their website. It was announced towards the end of last year, early this year. And even though it sounds a bit like a thing, National Timing Center sounds like a building somewhere, it's actually a program. It's actually to promote training, education and outreach, to promote skills within the UK around time, frequency, generation, distribution and dissemination, to fund projects via Innovate, so grant projects for technology, and to build out secure timing infrastructure. So we have partners that were announced in the press release, NPL, BT, the BBC, and some of the universities that are participating in the quantum clock research, Strathclyde, Birmingham and Surrey. And of course, there's a new product category that's recently been renewed. So there's these new boxes that are being described as GNSS firewalls. So I think there's 2 or 3 manufacturers that are promoting these as a way to protect already installed base of GNSS receivers. And it works just like an IT firewall. It sits between the danger zone, the sky signal where there might be hackers and spoofers, and your critical national infrastructure. And it contains a lot more in-depth signal analysis, and it contains a simulator as well. So it can ignore the signal from the sky and generate a timing signal that the installed base of timing receivers can use. This is where it would be situated. So we have a time sync server, maybe NTP or PTP time server. The GNSS firewall sits here. The validated output is the sky signal. So it does some analysis. It looks, one of the things the open source spoofers do, if you look, the default fields, the default data in the navigation message is not changed. So it's relatively easy to spot some of those less sophisticated spoofing attacks. If the GNSS firewall detects that, it will cut this signal off. So again, this validated output is the sky signal. If it detects something wrong, it can cut this signal off, and then you rely on the holdover of your time server. Next mode of operation is the so-called hardened output, where this is the simulated output. So again, the firewall looks into the received signal. If it detects anomalies, it can then generate its own GPS-like signal. So your installed base, you don't have to worry about going into all the existing deployments or finding where these timing receivers are embedded to replace them. You can just deploy one of these GNSS firewalls at one site to effectively protect all those receivers on that site. The third mode of operation on this slide is really there just for reference, only for monitoring. So if you just want to get some detailed analysis of what might be happening to GNSS signals, you can deploy this system with its management system, and it will look for position jumps, time jumps, look for anomalies in the data and things like that. So these GNSS firewalls are a relatively recent new product category. So to summarize, in terms of critical infrastructure, in terms of modeling failures, test and test again, always audit with time in mind. Where is time coming from? What systems do you have that rely on time? Don't forget the clocks. Don't assume that time is just there. We sometimes take it for granted, especially where there are trust algorithms, whether it's something like building access, whether it's logging onto computer systems. If there's a trust algorithm that uses time, it's susceptible to attack. There will be legacy dumb timing receivers around for many, many years. So we've got to somehow come up with a way of protecting those. Maybe GNSS firewalls are a way of doing that. And the whole cybersecurity audit process should consider signal spoofing for satellite timing as an attack vector. So if you've got any cybersecurity audits going on, ask the pen testers what they're doing, if they're capable of spoofing time and testing it. So thank you very much.